Introducing the swarm of art. Team 5, 4 burnt fuses. Our team is Graham Lane, that's me, Chris Valdez, and Chris O'Connor. Problem statement. Develop a system for art or performance to entertain 10 to 50 people for up to half an hour. Capitalize on the interest in AI art combined with performance creating unique physical art where digital art is limited to screen viewing or printing. Customers would be artists, art teachers, gallery owners, public engagement departments at art museums, STEM program coordinators, children's and science museums, summer camp programs, and after-school programs. Design requirements. The design shall be able to identify workspace and its boundaries. The design shall apply paint to the canvas or defined area. The design shall work for a set amount of time. The design shall be influenced by its surroundings. Apply more or less paint when it detects noise. Apply more or less paint when it detects changes in light level. React to temperature. Avoid drones to prevent damage. The design shall be able to withstand the effects of paint. The individual robots. Robot number 1, Fling and Dots by Graham Lane. Flings paint and drips dots on the ground based on the environmental inputs. Robot number 2, URO by Chris O'Connor. Forced air proximity reactive system for manipulation or accelerated drying of an art piece. And robot number 3, Paint Applicator, a Roomba-like paint dispenser. I'm Graham Lane, and this is Robot 1, Fling and Dots. It's a turtle shell design made out of blow-molded HDPE for easy cleanup and low cost. There's a proximity sensor for direction and obstacle avoidance, and a sound sensor controls the front media actuators. On the back is an annex for expansion, and 2 media tanks are on top. The flow chart and design changes. When you start the robot, it moves forward until it gets within 6 inches of an object. It backs up for half a second, turns forward for half a second, and as long as there's nothing in the way, it goes back to driving straight. It's constantly monitoring the sound level to change the tilt servo and the oscillation servo in the front. The number of sensors was reduced from earlier versions, leaving room for an expansion in the back. Cost savings and complexity were a consideration. Here are the schematics and the Arduino modeling. Here's the Arduino code. Proximity for the obstacle avoidance, and the sound sensor changes the 2 servos motors simultaneously. The robots will avoid each other through proximity detection. For the Arduino demonstration, you can see how the proximity sensor causes the drive motors to change direction, back up, rotate, until they reach a point when they have room to move. There's a blue dot in the center of the breadboard. That is a potentiometer that is substituting for an audio sensor. When you change the potentiometer, it changes how these 2 tilt servos in the front work. One of them changes its position based on the audio. The other one changes the angle width for the oscillation. In the serial monitor, you can see both the loudness level change and the proximity sensors readings. They work independently and constantly through the entire painting process. Thank you for watching Robot 1's demonstration.
My name is Christopher O'Connor, and as part of the Swarm of Art project for our Internet Engineering class in summer of 2023, what we've done is develop a system for art and or performance pieces to entertain the crowd, while also using the current interest in AI art and drones to get everyone watching while we make a unique, real, physical piece of art. As you can see in this slide from my design, the URO, the Universal Rolling Object, as it were, it's approximately 13 inches around. I've scaled this up a little bit for the diagram, be about 8 inches top to bottom. It's a very simple design, but very adaptable. Uses the air pressure from the main fan to either alter the paint if it's not dry or to help dry the art depending on the settings. You also have your proximity sensors to prevent it from running into either the other drones in the swarm or for leaving the boundaries of the art piece. Opting for a very maneuverable tank style drive system, the right or left, depending on which one or both is active, it makes it turn very easily. The outlet tubes for the air can also optionally be used to have valves to direct the airflow, or you can attach other paintbrushes, markers, things like that to them, help completely customize it or control how much or how little air comes out of this. The camera mount has been placed at the center to give you an optimal view. You can actually watch the art piece being made in real time from the view very close to where it's happening. As you can see in this slide, it shows you a little bit more detail from inside the battery compartment and where the CPU and other important things are housed. Is all within the dome, shielded from the outside paint from the other members of the swarm. If you look inside here, you can see that the fan itself is also will be completely covered by that. As I was mentioning, the inline motors here for right and left pretty much give you a 0-degree turning radius to help you from running into both the other drones who are leaving the area. The wheels optionally can also be customized a little bit. You can have different shapes or different coatings on them to either need more paint or hopefully not stick to the paint as much. Ultimately, you could also opt for audio or photo sensors depending on the type of venue. You could use those to increase or decrease the speed of the fan or the motors themselves to have the drone move faster. As you can see in this slide, we have a basic layout of the control center for the drone. We've got both of your ultrasonic distance sensors here covering all of the front-facing area, the direction it's moving. Whenever one of these is triggered, the opposite side motor will shut down for 3/4 of a second to cause it to rotate away from where their obstacle or other drone might be in the way. As you can see in this slide, we've got a little bit of the details of the code. So a very simple loop, so it just causes it to run a consistent distant thing. And whenever one of them is triggered, as I was saying, if the right side is triggered, it will actually cause the left wheels to shut down for a minute. So it'll push the drone away from the direction of whatever obstacles is in front of it. Drive motors are inside. Everything I've made, I've tried to center around where the fan motor is, so the air will constantly be pulled in and help cool everything around the center of it. As you can see, the very basic design behind all of this is just whether or not there's an obstacle in front of the sensor. So as long as there's nothing blocking this, it will just continue to move forward until the design time runs out. This will keep it from running in anything. I've set the distance sensors to be a little over the distance from the center of the unit out to the outside, so there should be no collisions between any of the drones. I will also keep it far enough away that it shouldn't, by design, push any of the paint from the blowers back towards the other drones to cause any of them to block. In summary, this whole experience helped me to learn that there's a lot more testing and redoing than I am used to in this, but much more on the user end of things rather than the design end of things. Definitely learned that I should have made better use of my resources, my team members who have both taken far more college classes than I have. This is a very rough intro back to college for me, having been out of the game for over a decade. And I would definitely start everything earlier to give myself more time to make mistakes that occurred with most things along the way. It's in a rush nowadays, so I'm gonna get brand new ready to catch me.
Hi, my name is Christopher Valdez, and I'll be talking about robot number 3, which I have named the paint applicator. Basically, the best way I can kind of describe this robot, it's almost like a Roomba, but for paint. And instead of like a Roomba hitting something and then changing direction, it uses distance sensors to make those changes in direction. What it does, it applies the paint to the surface, either for other robots to manipulate with their brushes or with air or something else like that. Or it can also be just part of the final design with the paint on the surface. It's controlled by 3 distance sensors, controlling directions. It's going to have 2 motors driving the robot, 2 actuators, opening, closing, basically where the source of paint comes from. This is from the bottom view. It's a square design on the side. It's going to have the wheels. On the back wheel, it's going to be just a castered wheel that can kind of move in any direction that it wants to. It's going to be independent. It's going to be so it doesn't just tip over to the front. In the front, you have front forward sensor, distance sensor, and then on the sides, you have 2 other sensors. Up underneath it is you're going to have the servos. They'll actually turn whenever they turn. They're covering holes right now in this view. But once they turn, they're going to move away from those, exposing those holes, which that's where the paint comes from. You can control how much paint flow comes from those holes. Now, this is from the inside. The view, there's 4 compartments that hold up to 4 different colors of paint. As you can see, there's holes in each of the compartments. Those are being covered by the actuators, the servos on the bottom. So whenever they open up or they turn, it's going to move the arm, then turn, and it's going to allow the paint to freely flow from underneath the base. It's got 2 motors, 1 for each wheel. It's pretty simple. It just drives it forward. And then in the middle area there, it's just basically where all your wiring would be, where all the motherboard and stuff like that would be located. It's got a cover for protection. Again, it kind of just reminds me of a Roomba. Instead of it actually hitting something, whenever it comes close to another object, it's going to take those readings. It's going to make the appropriate decision. Usually turn right. Report something from the front, it's going to turn to the right. Which something to the left, it's going to turn to the right. Something important from the left, and it's going to turn to the right. These are the circuits. You got the 3 distance sensors. You got the 2 servos out there. You have the 2 main motors that turn the wheel. This is going to be the code for this particular robot. I have it set up to go within 12 inches of an object. So if there's something that comes within that 12 inches, it'll make its decision to make the appropriate adjustments. So it's got the distance sensors. It drives a robot, turns a robot, and again it opens the paint ports, uncovers those holes, which allows paint to gravity to just pull paint in. And basically, it just wants to avoid other objects or other robots in the area. This is the flow chart. Taking it from the sensor, turns the motors off, closes the servos, also closes the servos, and it covers those holes, which stops the paint. But basically, it kind of goes from sensor 1, if it's within that distance. If it's greater than a distance, the answer is yes, then it continues straight. If there's something in between that distance, it's going to stop the motor, the left motor, turn the robot to the left, and then again, it's going to stop the paint from flowing for 5 seconds, and does that at each sensor until it gets back to the front. This is a demonstration of the code and at work. The motor's turning. The sensors turn 90 degrees, which that would be connected to an arm, which would be covering the holes. So they would now be open. Each of the sensors. I have it for 12 inches. Within that 12 inches, it's going to stop the it's going to turn it. It's going to close the servos for 5 seconds. Then they turn back on. Again, each of the sensors are work independently. And if you have multiple sensors in different directions, it should stop it completely. And that's all there is. Thank you for your time.
Thanks, Christopher. Let's talk about the collective behavior of the swarm of art. A stanchion barrier will keep the robots from leaving the working surface and prevent the audience from entering the workspace. Stanchions are like what you see at museums that surround sculptures or paintings that you can't get close to. Each robot will work autonomously using onboard sensors to avoid crashing into each other or the stanchion barrier. The robots will paint or perform in response to environmental conditions. And the robots will be able to work continuously for 1 hour without replacing the rechargeable batteries. A remote control system could be used via phone, laptop, or tablet to start and stop the robots. Here's a collective flow chart and sketch of what the robots might look like. The robots are autonomous. The primary collaborative function is interacting with each other's paint media, avoiding impacts, and staying inside the stanchions. The entrepreneurial aspects are estimated costs of early adoption buyers would pay around $2,200 for a set. Materials and labor will be higher than similar devices because of their niche market. Benefits to buyers: sale of art produced and attracting customers through performance. Similar products would be RC cars or novelty robots that are not purpose-built for art production. Original design: Swarm of Art is a unique product for art making and performance entertainment. Summary: we have introduced the Swarm of Art, an art-producing group of robots designed to entertain an audience. We shared the target audience, individual robots, workflow, programming, and collective behavior. Lessons learned: working with a remote team requires constant communication. Plan and organize early. Divide and conquer. Identify strengths and take advantage of them. Next time, start earlier. Ask more questions and simplify rather than overcomplicate. There are references. Thank you for your attention, and I hope you enjoyed the Swarm of Art presentation.